Welcome, everyone. Today we discuss the solution to the problem 2.1 of Peskin and Schroeder textbook on quantum field theory. It will be about the electromagnetic energy and stress tensor, or energy and momentum tensor, and its properties. So it will be about electromagnetic or Maxwell theory, stress energy tensor, Good. So we already knew that Maxwell equations or Maxwell theory can be derived as Euler-Lagrange equation of this following action given by the Lagrange density of Maxwell theory, which is minus 1 over 4 if mu and u, if mu and u. If mu nu is defined as the electromagnetic tensor, is known as d mu a nu minus d nu a mu. Where a mu, as we said in the last video, is the dynamical variable in this theory, and it's actually a gauge field. And so generally for any, so far we have learned that for a scalar theory, scalar field theory, so for example, that's given by a Lagrangian density that's dependent on phi and d mu phi, then we can derive the Euler-Lagrange equation as, and also the energy momentum tensor as d mu nu is equal, T mu nu is equal to dl d mu phi alpha if I have like multiple scalar fields, d nu phi alpha minus eta mu nu, where eta mu nu is the Minkowski metric times the Lagrangian density itself. So now we can apply this formula for our fields here, the Maxwell fields, but we have to notice that now a mu is a vector in itself, so it also carries a space-time index, and so I have to use multiple indices when I derive the energy momentum tensor. So for Maxwell theory, we get the formula that T mu nu is equal to d mu a alpha d nu a alpha minus eta mu nu Lagrangian density. But great, and so we can apply that. So we get so the Lagrangian density is given as, so we have d mu a alpha. The Lagrangian density is minus 1 over 4 if rho sigma, since they have independent indices of the derivatives, times d nu a alpha minus eta mu nu minus 1 over 4 if rho sigma, Okay, so this is equal to I have here the same term multiplied. When I derive it, I will get a factor of 2. So I will get minus 1/2 if rho sigma d mu a alpha times if rho sigma d nu a alpha minus the other term, which is eta mu nu minus 1/4 if rho sigma. Great. So this is equal to, now if I derive if rho sigma, I have to write it explicitly. So I have minus 1/2 if rho sigma d mu a alpha d rho a sigma minus d sigma a rho times d nu a alpha minus the other term, which is plus eta mu nu over 4 f rho sigma f rho sigma. Great. So this is equal to, now if I derive this term, we have encountered this term before. I will get like Kronecker delta because I actually differentiate the same field but with different indices. So I'll get a set of Kronecker delta. So this will be equal to minus 1 half f rho sigma delta rho mu delta sigma alpha minus delta sigma mu delta rho alpha times d nu a alpha minus eta mu nu or plus eta mu nu over 4 f rho sigma f rho sigma. Good. So this is equal to minus 1 half f mu alpha d nu a alpha minus f alpha mu d phi a alpha. So I guess multiplied by d nu a alpha, but the stress tensor now will take different indices that are restricted by these Kronecker deltas. So I will get equal to and then there is plus eta mu nu over 4 f rho sigma f rho sigma. So this is equal to minus 1 half f mu alpha d nu a alpha. Actually, because d nu, if alpha mu is actually antisymmetric, so if I flip here, if I change the order of signs, the order of indices, I will get minus, so I will get 2 of them. So in the end, I will get minus f mu alpha d nu a alpha plus eta mu nu over 4 f rho sigma f rho sigma. And that's our end result for the electromagnetic energy stress tensor. And the weird thing we notice here is that this is not symmetric. Okay, so it's actually not symmetric as we have seen so far in the classical field theories. And in addition, it's also not gauge invariant. But of course it's conserved, but it's neither symmetric nor gauge invariant, because as we see, if mu alpha is antisymmetric, but d nu a alpha in general is not the same if I flip the indices of mu and a. But this term is symmetric, but this term is not symmetric. And it's also not gauge invariant because this is well known to be gauge invariant, but if now I add to alpha some scalar, then this will show up here and it will not be the same after the gauge transformation. Great, so what can we do? So one way to symmetrize and normally the symmetric to symmetrize d mu nu, we add an extra term, a derivative of an extra term, and the new tensor that one gets after symmetrizing is called the Belinfante Rosenfeld tensor, which is a symmetrized version of the energy stress tensor, and this will be, if I call it t hat, mu nu is actually the same as t mu nu plus adding a derivative d lambda of a function of k lambda mu nu, which is already given in the problem itself. We don't need to figure it out. Where, as said in the problem, k lambda mu nu is antisymmetric in the indices lambda and mu. Okay, so and it's also given in the problem that k lambda mu, that will make it symmetric, mu nu is equal to f mu lambda times a nu. So we have to differentiate this term with lambda and add it to the energy stress tensor to make the whole energy stress tensor symmetric and gauge invariant. So how do we? So let's do that. So as I said, now the new energy stress tensor is T mu nu hat is equal to the old one, T mu nu, plus lambda d lambda f mu lambda a nu, which is equal to, now I write it explicitly what T mu nu is. It's minus f mu lambda d nu a lambda plus d lambda f mu lambda a nu, and then the nice term f mu nu over 4 f rho sigma f rho sigma. Good. Let's differentiate now the term. So we get it's equal to, by the way, so first we get minus, so notice that first, notice that if mu lambda times d nu a lambda is actually given as, can be written as if mu lambda d nu a lambda, right? Which is equal to eta mu rho f rho lambda d nu a lambda. So if I want to lower the mu in this, I have to multiply by the Minkowski metric, and so I get, therefore, the energy stress tensor is equal to minus eta mu rho f rho lambda d nu a lambda plus d lambda f mu lambda a nu, where I differentiate now only the stress, the electromagnetic tensor. And why is that? Because now I have a product of two functions. If I differentiate a nu, okay, so I forgot one term, which is the one dependent derivative of a lambda. So I will get f mu lambda d lambda a nu, and then the last term, which is eta mu nu over 4 f rho sigma f rho sigma. Great. So now the modified energy stress tensor will be minus eta mu rho f rho lambda d lambda a nu minus d nu a lambda. I added up the terms that have f rho lambda as a prefactor. So I have here one term which has f rho lambda and eta mu and rho, and here also another term. Okay, right. And so I will get that term plus eta mu nu over 4 f rho sigma f rho sigma. Okay, so it has shortened up a little bit, and so I will get, now this is already in the definition, already as a definition of the electromagnetic tensor. So I will get is equal to minus eta mu rho f rho lambda f lambda nu plus eta mu nu over 4 f rho sigma f rho sigma. So that's my end result for the new for the modified stress energy tensor. And now we see that it has the nice property that it's actually symmetric. So it's symmetric because the second term is already symmetric anyway, but the first term, now we see it's proportional to something like d lambda. So if we take one component of a rho, d lambda a1 d mu a1 which is So let's write everything explicitly for one component to see that it's actually symmetric. So so we have d mu a1 d lambda a nu a1 minus d mu a1 d1 a lambda, where 1 is now the value of rho, but it's independent of rho. So we will get minus d1 a mu d lambda a1 minus d1 a mu d1 a lambda. Okay, so and as we can see, if we now exchange the for example, if we take mu lambda, so let's say mu is equal to 3 and lambda is equal to 2, we will get the terms minus d3 a1 d1 a2 minus d1 a3 d2 a1 minus d2 a1 d1 a3 minus d1 a2 d3 a1. And so if we exchange now 2 to 3, for example here 2 to 3, 3 will be up and 2 will be down. It's already given in the second term, so it will be equal to that, because this will flip to this, and this will be the first term. And similarly here, if now I flip 2 to 3, this is already here by 3 by 2 flip. So if I flip the 2 mu to 2 nu to 2 nu mu, I still have the same form, and it's symmetric. So indeed it's symmetric, and it's also eigenvariant, obviously. Great. So now next, the question asks us to find that the new form, T mu nu, really gives the physical quantities that we wanted it to give, which are the energy, the total energy of the electromagnetic field, and the Poynting vector. So if we look now at the 0, 0 component of it, and we can show it will really give us the total energy. So T0, which is a scalar, will be minus eta mu rho if rho lambda if lambda 0 plus eta 0 over 4 if rho sigma if rho sigma. Now eta mu rho is only non-zero if it's in the diagonal, so rho has to be also equal to 0. So we will get minus eta 0 if 0 lambda if lambda 0 2 p squared minus e squared, and so we get totally minus f0 lambda if lambda 0 plus so we get f0 lambda f lambda 0 plus 2 over 4 p squared minus e squared. So this 2 over 4 will be 1/2. And f0 lambda is already equal to the because we already saw it last time that this is the electric field. So f0 lambda times f0 lambda, so we'll give the E field squared. And so I will get E squared plus p squared minus e squared of half, which is equal to 1/2 E squared plus P squared, which is the energy of the electromagnetic field. So really we get what is required from the question. Okay, so now if we want to derive, so now we want to see what are the spatial components of this tensor, and we want to show that it will give us the pointing vector. So this is already by definition is equal to minus eta 0 rho f rho lambda f lambda I plus eta 0 I over 4 f rho sigma, which is equal to minus eta 0 0, as I said before, 0 lambda I, plus eta 0 I over 4 f rho sigma, which is equal to minus f0 lambda I plus eta 0 I over 4 times 2 the B field minus the E field squared, which is equal to minus f0 lambda I but first we notice here that because the eyes are spatial, so they are 1, 2, 3, and so on. So this metric tensor will vanish for such values. So we only get the first term, which is already equal to, so f0 lambda we said is the electric field, so minus E lambda f lambda I, which is equal to E lambda. But if lambda I is dependent, as it can be written as lambda A lambda IK pk. We saw that in the last video. And so we indeed have a cross product between an electric field component, or between the electric field vector and the magnetic field vector. So I can write it as E times P, which is already the definition of the pointing vector. And so we really get the required physical quantities even after we symmetrize the energy stress tensor.